Okay, so the topic for today is going to be parametric equations, and just to give us an idea of what a parametric equation is, let's contrast it with what we call a rectangular equation. So a rectangular equation is something that looks like this. Y is equal to x squared over 4 plus x. In this situation, y is a function of x. These are the normal equations that we're used to deal with. On the other hand, a parametric equation is actually a set of two or more equations, and here's an example. X of t is equal to 3 sine t, and y of t is equal to square root of t plus t squared. Okay, so what's the difference here? X and y are they depend on a third variable, but really what we call that is we call it a parameter. So they depend on a parameter t, which you can think of as time. So what we've effectively done is taken x and y and separated them apart so that they can move independently. So how do we deal with these? Well, the first thing we'll do is go ahead and graph. For example 1, let's assume I am asked to graph the following set of parametric equations. X is equal to t squared minus 4, and y is equal to t over 2. Okay, so how do we graph this? It turns out that when we actually do draw the graph of this, that we're only going to graph this in the xy plane. Okay, as with anything, when you first begin to graph it, a good thing to do is actually just to pick values. So what we're going to do is we're going to pick values of t, and after we pick values of t, we're going to calculate what the x value is at that time and what the y value is at that time. Just arbitrarily, we'll pick for time -2, -1, 0, 1, 2, and 3. If you plug in at t equal -2, it turns out that your coordinates are at 0, -1. Okay, so at time equal -2, where are you at in the graph? Here. And I'm just going to label that that's at time equal -2. Okay, at time equal -1, it turns out you're at -3, comma, -1/2. So roughly speaking, let's make this a little bit accurate, or try to make it a little bit accurate. You're at -3, comma, -1/2, so you're roughly here. I'm just going to label that t equal -1. Okay, at 0, if you plug in 0, you're at -4, comma, 0. Okay, so you're over here. I'm going to label that t equals 0. And then if you work out the rest, we'll just go ahead and write it down. You're at -3, comma, 1/2. Then you're at 0, 1. And then you're at 5, comma, 3/2. Okay, so if we go ahead and plot those points. If we plot -3, 1/2, you're up here. This occurs at t equal 1. T equal 2, you're at 0, 1. So this is equal t equal 2, and then t equal 3, you're way out here somewhere at 5, comma, 3/2. Okay, now why do I put the times? It's because when you graph a parametric equation, the direction that you graph matters. So in this example, I started here, I go over here, to t equals 0, t equal 1, t equal 2, and so forth to t equal 3. Okay, and you need to indicate direction by putting arrows. So this tells me the direction that the path goes. You can think of this like a particle that's moving in the xy plane that is governed by these two equations. Okay, go ahead and let's graph a second example. Let's look at the following set of parametric equations. X is equal to 1 over square root of t plus 1, and y is equal to t over t plus 1. Just for uniformity, we'll pick the following times. We'll pick negative 0.75, 0, 3, and 8. Okay, so go ahead and try graphing this on your own and see what happens. Okay, if you've gone ahead and graphed it, here are the coordinates, and what you'll notice is that the graph actually does something like this. Now, what's important to note, and you can tell by the x-coordinate, is because the x-coordinate will only be 0 as t is infinity, this will actually never reach x equal to 0. Okay, specifically here, when t is infinity, your y coordinate is 1 and your x coordinate is 0, but it takes an infinite amount of time to get there, so you will never reach 0, 1. You can actually check the graph on the graphing calculator if you just go ahead and change your mode to parametric or par instead of function, and let's keep it in radians. So now when you hit y equals, notice you'll have an x1 equals x2 equals. So let's punch in what we had. Our x was 1 over square root of t, so your x variable will now be a t when you push the button, t plus 1. And then on the bottom you had t over, in parentheses, t plus 1. Okay, so let's take a look at the graph. If you look at the graph, it goes in the direction that we expected, but it doesn't show the full graph. And the reason for that is we actually have to change our window because our t minimum was negative 0.75. Okay, and they go all the way up to, this is 2 pi, but let's see that the graph matches ours a little bit better there. Okay, so you can see that. Okay, a couple remarks regarding parametric graphs. First remark is that these parametric curves, I'll call them, have an orientation. Parametric curves have an orientation, or a better way to say that, or what might make more sense, is they have a direction. Okay, so it turns out you must draw those arrows. The AP test will actually take off points if you do not show the direction of the parametric equations. The second thing I would note is that some graphs are not functions. You actually saw that in the first example where we had sort of a sideways parabola, and so what you'll find is we actually have more freedom with parametric curves than we did with just plain old rectangular curves.